Okay, welcome to my, next IB video lecture. Basically, what we're going to be doing today is we're going to be starting or continuing this topic 5. So we're going to be kind of introducing you to thermochemistry. This is only the first part of it, so we're just going to be kind of talking about uh, entropy. Today, we're going to kind of try to define for some of you guys, and I'm going to be posting additional videos that you can watch to make you understand it. Understanding basically what state functions are, because these state functions are going to relate to what we're doing in the next lessons. We're going to talk about, Hess's law in the next video, and also calculating uh, the heat of the solution. So basically, yeah, we need to know these as a foundation for what we're going to be covering next. So basically, give me 1 second. We're going to get this set up. So basically what we're going to be covering is just, the first chapter of Unit 5. So if you've got the textbook, I really hope you read over that chapter. You don't need to cover the Hess's law in chapter 5.2, but 5.1 so far. And 5.1, we're talking about enthalpy. So enthalpy, which we write as H. So it's the delta H, and we're going to see a lot of different enthalpies. We're going to see standard enthalpies later on in this unit. We're going to see, enthalpy of formation, enthalpy of the reactants. We're going to see lots to do with enthalpy. So what we need to learn about enthalpy is that this is the word that we're going to have to start using. And enthalpy is a state function. So enthalpy is a state function, right? So what a state function is a state function is basically a variable that we can measure directly. So we can measure it directly. So I'll give you some examples, and then we're going to talk a little bit more after. So variables like volume, variables like temperature, variables such as pressure. And what we're going to see in this unit is we're going to see, a change in internal energy is also going to be a state function. We're going to have delta H is also going to be a state function. Delta G, which we're going to see later on, delta S, these are all going to be state functions. So it's basically something that we can measure directly. We can just take something and say, okay, how many milliliters do we have, right? We've got our change in volume. We can measure by doing change in volume of the final solution. The volume of the final solution minus, not the change in, minus the volume of the initial solution. So we can figure out directly how much volume was added. We can figure out what is the final volume. We can measure what was the initial volume. So we can measure these values directly. So the way that people like to define this, the way that your textbook is going to define this, if we just make a graph, right? So a state function, what it does, it does not depend on the path taken. So let's just write that up here. I'll just write it up here in red. So a state function. I'm going to post more videos on this too, because it is a very important part to understand. So it does not depend on the path taken. So I'm going to use this graph right down here as an example. So let's say we have a graph, temperature versus time throughout the day. Time in, let's just say, hours, and temperature, we'll just use degrees Celsius. So let's just say we're this is a swimming pool. So we'll say temperature of pool over a day, over the span of a day. So the pool, right? You go and you measure the temperature of the pool at 10 a.m. So we'll just, 10 a.m. So you measure it, then we're going to say 11's here, 12, 1, 2, 3, 4, 5, 6, 7. So, you're a pool employee, and basically you measure at 10 a.m. and your boss says, okay, we need you to measure it at 10 a.m. and 7 p.m. every single day to make sure that the temperature is constant. So, you take a measurement right here, you say, okay, good, it's at 25 degrees Celsius, that's where we want it to be. But then during the day, right, the sun's coming up, so the temperature might be increasing a little bit, and the sun starts to go down. The temperature can maybe fluctuate a little bit below, and then come back up. So we measure it again. Let's just pretend like this is 7 p.m. And we say, okay, it's at 25 degrees Celsius. So you just make the conclusion, okay, the pool's been at 25 degrees Celsius all day. So you've taken your initial, your final, minus your initial, and found that there's no changes, even though throughout the day there have been some changes in the system. So that's one example of what a state function is, right? We measure the final and the initial, and we can measure the change in it. We can measure, we can perfectly measure the temperature at one point, and we can measure the temperature at another point. So basically, a second example, I have a few of them written down here of state functions. Is a state function would be, if you live here in Mexico, or you live here and you go to work right here, right? So the direct distance from you to work, the flight distance, the sky distance, let's just say the distance is 10 kilometers. The direct distance from you to work. So the distance is 10 kilometers. But depending on the path that you take, the distance that you traveled is different than this. So the state function of this is that the distance from you to work is the same every single time. It's always 10 kilometers direct distance. But then we can, in contrast to what a state function is, there's something called a path function. And I always write function like this, a path function. And this basically depends on how you get to work, right? So the distance you travel is different from the distance of you directly to work. So a path function, right? We can walk, we can drive, we can take a bike. If we want to, we can jog to work. And all of these expel different amounts of energy. There's a different amount of force you need to travel that distance. So all of these take different amounts of work. So work in this case is a path function. The amount of energy, the state function is the distance from you to work. And the path function is that, you walk to work, you're not going to expel that much energy, right? You can maybe take a nice path, skip through a few backyards like we used to, and then arrive at work. And, you've traveled, 11 kilometers in total, let's just say. 11 kilometers walking. But if you drive, you're going to expel less energy. So the energy that you expel, the work that you expel as a person is different. Because, right, you can get in your car and you expel almost no energy. You wake up in the morning, you down your cup of coffee, you run to your car as fast as you can. You drive a little clown car, I guess. You jump in the clown car and you drive to work. So you're spending less energy, but you might be going a larger distance. Maybe now you've doubled the distance to work. You've gone 20 kilometers because there is no direct way to get to work. If you jog, you're going to expel more energy than this if you walk. If you bike, more than if you walk, but possibly less than if you jog, depending on the pace that you're biking at. So basically, the state functions only depend on the final and the initial conditions, whereas path functions depend on the path that you take to get to that final and that initial positions. And we're going to be going over how this relates to chemistry soon, but just, I'm just trying to get you into the mindset that state doesn't care about the path that we take, and path functions do care. The amount of work is different, or the amount of heat that our bodies produce is different, right? So Q is also a path function. So Q is also a path function, right? If we drive, our body's going to produce a lot less heat and release a lot less heat to the surroundings. But if we walk, we'll a little bit more heat. If we jog, a little bit more heat. And if you're like me, if you ever were biking, your body releases a ton of heat. So the heat is different and the work is different. So heat and work are both examples of path functions, whereas mostly everything else that we're going to be measuring in this unit, volume, temperature, pressure, change in internal energy, Gibbs free energy, our delta H values and our entropy, our enthalpy and our entropy are all going to be state functions. So they're not going to depend, they're only going to depend on the initial and the final state, and it doesn't matter how you get there. So a good example that I like to show of that is, I've got the slides, I've got the slides right here. And basically, right, here's two different paths that we can go through. We can either, have this already in solution, sodium and chloride ions already in solution, evaporate off the solution, and the enthalpy of formation is just gonna, they're gonna come together and release 411 kilojoules. Or we can take the second path, right? And the second path takes a lot more steps, but our overall change in energy is gonna be the exact same, right? We're gonna take, our sodium solid and chlorine gas, and then to react them together, we're going to add some energy and change sodium into a gas. And then from there, we're going to, break apart the chlorine-chlorine bond, which is going to take more energy. Then we're going to ionize them. So we're going to hit this with an electron gun. And basically, hopefully this chlorine will capture one of the electrons. And then once we're in that phase, finally they can react together to form sodium chloride. So the sum, if you take out your calculator right now and you add all of these values together, we're going to come out to the same value, that both paths still have a change in enthalpy of 411 kilojoules, even though the work, right, the work that you'd have to do as a chemist through these steps are much different. And the heat that you need to add to the systems are much different too in these circumstances. So yeah. So let's continue on. Another one example that I'd like to go through for this. This is the example my uni prof went through back in the day. I forget exactly what his name was, but I remember that he sounded a little bit like Kermit the Frog, so it was pretty good. Let me just erase this real quickly. There we go. So another one that I like to imagine, another path versus state function. A state function would be, right, we've got a tall mountain. So a very tall mountain, and you and your friends, set out one day and you say, okay, we're going to climb up this mountain. And this other group over here, maybe a little bit less adventurous, says, we're just going to take that gondola up the mountain. Why would we walk for 4 hours when we could take the gondola for 30 minutes and be at the top? So we've got the gondola right here, and this guy takes the gondola and you decide to walk. So the change in your elevation, right? You go from sea level maybe up to something like 2,000 meters. You guys are both going to go through this change. So your final, altitude versus your initial altitude is going to be the same for both of you. So that is a state function where we can characterize the final altitude, or altitude final. We can minus off our altitude initial, and we could solve the change in altitude. Whereas the heat added to a system, right? There's not a change in heat added to a system. It's just how much heat you added to a system. If you imagine something like, let's see how we can imagine this. If you just look at a block of limestone, right? You can't just look at that block of limestone and say, how much heat does it have? How much heat? Right? That doesn't make any sense. How much heat? We can talk about, the problem that we can't do is we can't confuse temperature with heat. Heat is the total kinetic energy of every single molecule in this system. whereas temperature is the average kinetic energy of all of the molecules. So we can't directly measure heat. We can measure how much heat we've added. So we've added some sort of amount of kilojoules. We can measure how much heat we've lost to the surroundings. But we can't just take something and say, how much heat does this have? What's the sum of all of the energy, or all of the kinetic energies all of the molecules, all the thermal energy of the molecules in this square? So that doesn't really make any sense. And same thing with work, right? We can't really say, look at this same square and say, what's the work of this square? Right? That doesn't make any sense. If the square changes, if we expand that square, and let's say it's made out of some sort of material that can stretch, now the gas on the inside has done work. Work is just force multiplied by distance. So we've seen a change in distance with some sort of applied force. So we know that work has been done. And we could just say, how much work has been done? We can't say, what is the change of work of a system? What was the original work here, right? There's no change in distance, so there's no initial work. It's just the work is a change. So work causes a change. We can't just measure that change directly. We can't just say, what's the final work? What's the initial work? And let's figure out how much work has been done. We can say, okay, what's the final, what was the final displacement of that box expansion? That makes a little bit of sense to measure your work. So let's go back to this example. So basically, he takes the gondola up to the top. So he is performing, a very small amount of work. He's walking here, which is, he's moving, so he's applying a force from his body over a distance. But then in here, he's just sitting down. He's doing zero work to get to the top. Whereas this person, right, you have to, if you've ever climbed a mountain before, typically you need to swirl around the mountain basically all the way to the top, because you can't just walk directly up this mountain. It's going to be too steep. You're going to fall down and you're going to end up right where you started. Usually it's a nice path all the way up the top. So it's basically a force times the distance, how much force you were applying at each moment, divided by the distance that you traveled, the distance that you've pushed your own body. So that is the work. We can't just, take the final state and calculate the work. So what's another one that I can do? So basically the question that I like you to ask to figure out whether it's a work function or a state function is good question, is do I care? Do I care about this lesson, right? I'm kidding. But it's, do I care how I ended up at the final value? How I ended at the final value. So, right, do I care how I ended at the final value? If the question is just, what's the change in altitude? Nobody cares. It's you don't care how you ended up at that final. You don't care if you walked. You don't care if you bike rode. You don't care if you put a little helicopter on side and you flew up to the top of the mountain. The person asking the question, it doesn't matter. What is the change in altitude? That's what's important. Whereas if somebody were to ask you, how much energy in calories did you expel getting up the mountain? Then that's a path function. That depends on whether you walked up the hill, or it depends whether you just paid the $20 and you took the gondola up the hill. So that's the difference between a path and a state function. A state function doesn't care, and a path function cares. So okay, let's see what else we can cover for this unit. And then we're going to relate, why do we care about the difference between a path and a state function, and why, when I do this next video on Hess's law, you're going to see what's so useful about something being a state function, what calculations it can simplify. Let me just make sure. There we go. That's nice. So basically, just to we'll finish off for the day, is we're going to define what is thermochemistry. So that's basically what we're talking about. Thermodynamics, thermochemistry. It's basically the study of heat changes, the study of heat during chemical reactions. So we want to know what is the, how much heat we had to add at each step, how much heat was lost at each step. So that's heat, right? That depends on the path. But then the final, right? If we were just calculating something like CH4 plus O2 forms CO2 and H2O. If we were just doing that, right? If we calculated the delta H reactants, or H reactants, H products, we know that our delta H is equal to delta H is equal to H of react minus H of products. So we've got the final. We can calculate the final and the initial based off of the bond strengths. But then if we were to change states, right? If we went from, CH4, if one of them, you cooled down, CH4 started as a solid, we need to add some heat in order to cause CH4 to go to a liquid. Then we'd have to add some heat for CH4 to go to a gas. So we're adding different amounts of heat in order to get the exact same reaction, right? So the path through the reaction will change the heat and will change the work of the system. But in the end, our delta H's will be the same. We can just calculate the bond energy of what was formed versus what was reacted and calculate the change. So give me a second, my headset's just dying. I'm going to plug it in real quick and I'll be right back. There we go. Okay, so we're good. So the last one that I'd like to do, so the one more term that I'd like to kind of cover for this unit is we want to say the change of enthalpy. So the change of enthalpy. What we're going to start seeing through here, right? We before in IGCSE, you always did delta H and your values were in kilojoules per mole. What we're going to be seeing here is that now that we've done the stoichiometry unit, we know the amount of moles. We know that there's 2 moles for some reactions. We know that there's 1. We know that there's 0.5. So what we're going to be doing is we're going to be calculating the delta H of the reaction. So we won't just be calculating the delta H in general to figure out what is the kilojoules per mole of CO2 formed, what are the kilojoules for moles of water formed, or what's the enthalpy change for this whole reaction. You're going to actually get real values, and we're going to calculate what is just the heat, what is the Q, how many kilojoules of energy did this reaction in particular release, or that this reaction in particular absorbed. So this change of enthalpy, we also call it, another word for it, sorry, I haven't changed colors at all this time, oh no. So we also call this the heat of reaction. And this is specific. So it's specific to the reaction and the conditions that we used, and the units are going to be kilojoules instead of kilojoules per mole, because now we're taking into account how many moles that we had. So aside from that, I will post some extra, hopefully additional videos that might clarify the difference between a state and a path function and how it relates to chemistry. But overall, what we just need to understand is that a state function, we just take the final and the initial values, and we don't care how we got there. So that's just like that web page I just showed you guys where, one reaction path had 10 different parts of the reaction, and one had 1 part, but we still have the same energy change of 411 kilojoules per mole, and we still have the same energy, 411 kilojoules per mole. So we see that no matter what path we take, our enthalpy change stays the exact same, and that's why this is considered a state function. But each of these different parts of the path are part of a path function. We can calculate the Q and we can calculate the work done through these paths and compare them, and they will be different. Okay, so the last one that I'd like to, actually, I don't need to cover anything else. So hopefully this video helped a little bit with defining what's the difference between a state and a path function. I'll see you in the next one.